numbers. Real numbers. So first we need to discuss about the prime numbers. What is prime number? A positive integer p is considered a prime number if case 1 p is greater than or equal to 1 and p does not have any factors other than 1 and p, so that a is equal to b into q plus r. Next, composite number. A number greater than 1 and not a prime number is a composite number. Fundamental theorem of arithmetic. Every composite number can be expressed as a product of primes, and this factorization is unique except for the order in which the prime factor occurs. Next one, irrotational number. If a number cannot be written in the form of p by q, where p and q are integers of a. Example, root 2 comma root 3 comma root 5. Here q is not equal to 0, p and q are co-primes to each other. Next, if a prime number p divides a, then p divides a. So where a is a positive integer. So two numbers a and b are said to be co-primes if only common divisor of a and b is 1. Next, Euclid's division lemma. Given positive integers a and b, or there exist unique integers q and r satisfying the given equation. A is equal to b into q plus r. 0 is less than or equal to r less than b. So dividend is equal to divisor into quotient plus remainder. So fundamental theorem of arithmetic. Every composite number can be expressed as a product of primes, and this factorization is unique except for the order in which the prime factors occurs. Next, if A is divides BC and HCF of AB is equal to 1, then A divides C. If a prime number divides the product of two integers, then it divides at least one of them. If D is the HCF of two numbers x and y, so a comma b belongs to z, such that ax plus by is equal to b. Exercise number 3.1. Problem number 1. Use Euclid's division algorithm to find the HCF of the following numbers. Problem number 1, 65 and 117. So by using Euclid's division lemma, a is equal to b into q plus r. So step 1, here a is always bigger value 117 and b is equal to 65. So 117 is equal to 65 into 1 plus remainder is 52. Step 2, a is equal to 65 and b is equal to 52. So 65 is equal to 52 into 1 plus 13. Step 3, a is equal to 52 and b is equal to 13. So 52 is equal to 13 into 4 plus 0. So from the step 2, 13 is the last non-zero remainder. So its HCF of 65 and 117 is 13. Next problem, use Euclid's division algorithm to find the HCF of the following numbers. Number 2, 237 and 81. By using Euclid's division lemma, a is equal to b into q plus r. A is equal to 237 and b is equal to 81. 237 is equal to 81 into 2 plus 72. Step 2, a is equal to 81, b is equal to 72. So 81 is equal to 72 into 1 plus 6. So a is equal to 72, b is equal to 6. 72 is equal to 6 into 12 plus 3. Step 4, a is equal to 6 and b is equal to 3. So 6 is equal to 3 into 2 plus 0. From the step 3, so 3 is the last non-zero remainder. So hence HCF of 237 and 81 is 3. Next third one, 55 and 210. Step 1, A is equal to 210, B is equal to 55. 210 is equal to 55 into 3 plus 45. Step 2, A is equal to 55 and B is equal to 45. 55 is equal to 45 into 1 plus 10. Step 3, A is equal to 45, B is equal to 10. So 45 is equal to 10 into 4 plus 5. Step 4, A is equal to 10 and B is equal to 5. 10 is equal to 5 into 2 plus 0. So from step 3, 5 is last non-zero remainder. So hence HCF of 55 and 210 is 5. Next one, 305 and 793. By Euclid's division, A is equal to B into Q plus R. Step 1, A is equal to 793 and B is equal to 305. 793 is equal to 305 into 2 plus 183. Step 2, A is equal to 305 and B is equal to 183. 305 is equal to 183 into 1 plus 122. Step 3, A is equal to 183 and B is equal to 122. 183 is equal to 122 into 1 plus 61. Step 4, A is equal to 122 and B is equal to 61. So 122 is equal to 61 into 2 plus 0. So from step 3, 61 is last non-zero remainder. Hence HCF of 305 and 783 is 61. Next problem. So that any positive even integer is of them 4q or 4q plus 2 where q is whole number. So let A be an even positive integer. Applying Euclid's lemma, if B is equal to 4, so A is equal to 4 into Q plus R. R can take value 0, 1, 2 or 3. But A is even integer, hence R is equal to 0 or 2. Hence A is equal to 4Q or A is equal to 4Q plus 2 respectively. So these are the even positive integers. So next problem, use Euclid's division lemma to show that the square of any positive integers is either of the 3m or 3m plus 1 for some integers m but not of the form of 3m plus 2. So let A and B two positive integers. So Euclid's division lemma is A is equal to B into Q plus R. So consider B is equal to 3. So A is equal to 3Q. A square is equal to 9Q square. So A square is equal to 3 into 3Q square. A square is equal to 3M. So M is an integer. Consider A is equal to 3Q plus 1. A square is equal to 3Q plus 1 whole square. So 9Q square plus 6Q plus 1. 3 into 3Q square plus 2Q plus 1. That is 3M plus 1. So where M is a integer. Next, case 3. A is equal to 3Q plus 2. So A square is equal to 9Q square plus 12Q plus 4. So A square is equal to 3 into 3Q square plus 4Q plus 1. So 3Q square plus 4Q plus 1. So M is an integer. So square of any positive integer is of the form of 3m, 3m plus 1 and not 3m plus 2. Prove that the product of three consecutive positive integers is divisible by 6. Product of three consecutive positive integers is given by n minus 1, n plus 1. So case 1. When a number is divided by 3, then n is equal to 3p or 3p plus 1 or 3p plus 2. So if n is equal to 3p, n n is divided by 3. If n is equal to 3p plus 1 and n minus 1 is divisible by 3. So if n is equal to 3p plus 2, n plus 1 is equal to 3 into p plus 1, which is divisible by 3. N minus 1 comma n plus 1 is divisible by 3. Case 2. When a number is divisible by 2, n is equal to 2q or 2q plus 1. So n is equal to 2q, so n is divisible by 2. If n is equal to 2q plus 1, both n minus 1 is equal to 2q and n plus 1 is equal to 2 into q plus 1 are divisible by 2. So n minus 1 comma n plus 1 is divisible by 2. So from the both case, n minus 1 n plus 1 is divisible by 2 and 3. So it is also divisible by 6 also. Find the LCM and HCF of the following integers by expressing them of the product of primes. 12, 15 and 13. Prime factors of 12 is equal to 2 square into 3. 13 is equal to 3 into 5. So 30 is equal to 2 into 3 into 5. So LCF is equal to 3. LCM is equal to 2 into 2 into 3 into 5 is equal to 60. Next one, 18, 81 and 108. Prime factors of 18, 81 and 108. 18 is equal to 2 into 3 into 3. 81 is equal to 3 into 3 into 3. So total 3 to the power of 4. 108 is equal to 2 square into 3 cube. HCF is equal to 9 and LCM is equal to 2 into 3 cube 3 power 4. 2 into 3 power 5 is equal to 3 to 4. Sixth problem. There are 75 roses and 45 lily flowers. There are to be made into buckets containing both the flowers. All the buckets should contain the same number of flowers. Find the number of buckets that can be formed and the number of flowers in them. Solution. All buckets should be contain the same flowers. So we need to find out the HCF of the numbers. HCF of 75 and 45. A is equal to 75 and B is equal to 45. So A is equal to B into Q plus R. 75 is equal to 45 into 1 plus 30. Second step, 45 is equal to 30 into 1 plus 15. So next step, 3 is equal to 15 into 2 plus 0. So second step is our HCF. So number of buckets is equal to 15 and number of flowers is equal to 120 by 15 is equal to 8. Next, the length and breadth of rectangular field is 110 and 30 meters respectively. Calculate the length of the longer rod which can measure the length and breadth of field exactly. So they are given length and breadth. So by using Euclid's division lemma, we need to find out the HCF of the 110 and 30. So HCF of 110 is equal to 30 into 3 plus 20 is remainder. 30 is equal to 20 in 20 into 1 plus 10. 10 is remainder. 20 is equal to 10 into 2 plus 1. So 10 is last non-zero remainder. So longest rod required is 10 meters. Next one, exercise number 3.2. Express each number as a product of prime factors. 120. We need to written as prime factorization method 2 cubed into 3 into 5. Second one, 3825. 3 square into 5 square into 17. Now 6762. 2 into 3 into 7 square into 23. Next 32844. 2 square into 3 into 7 into 17 into 23. Next, if a number 25025, find the values of P1, P2, P3, P4 and x1, x2, x3, x4 by using prime factorization method. 25025 is equal to 5 into 5 into 7 into 11 into 13. So 5 square into 7 to the power of 1 into 11 to the power of 1 into 13 power of 1. So P1 is equal to 5, P2 is equal to 7, P3 is equal to 11 and P4 is equal to 13. So x1 is equal to 2, x2 is equal to 1 and x3 is equal to 1 and x4 is equal to 1. Next problem. Find the HCF and LCM of pairs of integers and verify the LCM of A into B into HCF of A into B is equal to A into B. So 16 and 80. Solution. 16 will be written as 2 power 4 and 80 is equal to 2 power 4 into 5. So HCF is equal to 16. So LCM is equal to 24 into 5 is equal to 80. So thus HCF into LCM is equal to A into B. So 60 into 80. Second one, 125 comma 55. So 125 is equal to 5 cube. 55 is equal to 5 into 11. So HCF is 5 and LCM is 5 cube into 11. 1376. So HCF into LCM is equal to A into B. So 6875. If HCF of 52 and 182 is 26, find the LCM. HCF of 52 and 180 is given as 66. So A into B is equal to HCF into LCM. LCM is equal to 360. Find the HCF of 105 and 1515 by prime factorization method, and hence the find its LCM. HCF of 105 and 1515 is 105 is equal to 5 into 7 into 3. 1515 is equal to 5 into 3 into 105. So HCF is equal to 15 and LCM is equal to 5 into 3 into 7 into 105 is equal to 10,605. 7. Find the smallest number which when increased by 17 is exactly divisible by both 520 and 468. So prime factors of 520 and 468. 520 is 2 cubed into 5 into 13. 468 is 2 square into 3 square into 13. So LCM is 2 square into 3 square into 5 into 13. So 4680. So the least number is 4680 minus 17. So 4663. A rectangular hall is 18 meters 72 centimeters long and 13 centimeters 20 centimeters broad. It is to be paved with square tiles of the same size. Find the least possible numbers of such tiles. So we need to convert a meter into centimeter. So rectangle hall is 1872 centimeters long and breadth is 1320 centimeters. So HCF is 1872 and 1320. HCF is 24. So 20 meters 24 centimeters size tiles are required. Area of wall is equal to 1872 into 1320. 2471040 centimeter into centimeter centimeter square. So area of each tile is equal to 576 centimeter square. So minimum number of tiles is equal to area of hall by area of each tile. So 4290. In a school, the strength of 8th, 9th and 10th standards are respectively 48, 42 and 60. Find the least number of books required to distribute equal among the students of 8th, 9th and 10th standard. So 8th standard is 48, 9th standard is 42, 10th standard is 60. Prime factors method. 48 is equal to 24 into 3, 42 is equal to 2 into 3 into 7, 60 is equal to 2 square into 3 into 5. So LCM is 1680. Least number of books required is 1680. 10th one. X, Y and Z start the same time in the same direction to run around a circular stadium. X completed a round in 126 seconds, Y in 154 seconds, Z in 231 seconds. All starting at the same point. After what time will they meet at starting point? How many rounds would have X, Y, Z completed by this time? X is 126 seconds and Y is 154 seconds and Z is 231 seconds. So the LCM of 126, 154 and 231 is 1386. So they will meet again after 1386 seconds. X will have completed 11 rounds, Y will have completed 9 rounds. Z will have completed 6 rounds. So 6 rounds and 126 seconds. Exercise number 3.2. Prove that root pi is an irrotational number. Solution. We use the method of contradiction to prove. Let us first assume the number is a rational number. There is integer p and q such that where p and q are co-primes to each other, squaring on both sides, 5 is equal to 5q square. Q square, we can say that 5 divides p square and hence p. P is equal to 5k. Replacing 5q square is equal to 25k square, where k is an other integer. So q square is equal to 5k square. Hence 5 divides q also. But this is a contrary to that assumption that p and q are co-primes to each other. This implies the assumption is wrong. So therefore, this is a irrotational number.